learning objectives for this video. Covalent bonds involve the sharing of electrons, but those electrons aren't always shared equally. With polar covalent bonds, the bonding electrons are attracted more strongly to one atom than the other, and therefore the electron distribution between the atoms is not symmetrical. And in the continuum of bonds, we have the covalent bond over here where we have a perfect sharing of electrons, and then we have the polar covalent bond here where there's an unequal sharing, and then at the other extreme we have the ionic bond where one atom has completely taken an electron from the other atom. The reason polar covalent bonds arise are because of differences in something called electronegativity, which you probably heard about in general chemistry. Electronegativity is simply the intrinsic ability of an atom to attract the shared electrons in a covalent bond, and the differences in electronegativity produce bond polarity. Fluorine is the most electronegative element in the periodic table, and cesium is the least. And the metals on the left side of the periodic table tend to attract electrons weakly, whereas things on the right side attract electrons strongly. Carbon, which is the foundation of organic chemistry, has an electronegativity value of 2.5. In comparison, fluorine has an electronegativity value of 4. The higher that value, the higher the electronegativity. Here is a table of electronegativity values. The higher the number, the more that element wants electrons. So you can see the highest number here is a 4. That is assigned to fluorine, and that means fluorine is the most electronegative element. And if you notice, the elements on the right-hand side are a lot more electronegative than the elements on the left-hand side. There's some general rules we can use here. If you have a bond between two atoms and the difference in the electronegativity values between those two is less than 2, you probably either have a polar covalent bond, and if it's a very small difference, you have a nonpolar bond. If the difference in electronegativity is greater than 2, then you've got an ionic bond. In this class, we're going to see a lot of carbon-hydrogen bonds. That electronegativity difference is about 0.4, which is pretty small. So we consider those to be essentially nonpolar bonds. In contrast, carbon-oxygen and carbon-halogen bonds, like carbon-fluorine, carbon-chlorine bonds, are polar. When you have a polar bond, the more electronegative atom pulls the electron density towards itself, and therefore you have the other atom with a partial positive charge and the electronegative atom with a partial negative charge. This results from what's called the inductive effect, where the electrons in that sigma bond are shifted closer to that more electronegative hungry atom. Molecules can be overall polar if all of their polar bonds don't cancel each other out. And if a molecule is polar, it will have what's called a dipole moment, which is the magnitude of the charges at the end of the molecular dipole times the distance between the charges. So here are some polar molecules and their representative dipole moments. In the arrow drawn by each one, the head of the arrow points towards the partial negative end of the molecular dipole. Some molecules have polar bonds, but they don't have a dipole moment. Carbon dioxide is the prime example of this because both of the CO bonds are polar, but they are in completely opposite directions, so they actually just cancel each other out. So with symmetrical molecules that have polar bonds, the dipole moments of each bond can cancel each other out, which will lead to an absence of a dipole moment for the whole molecule. At times it's necessary to have structures with formal charges on individual atoms. So for example, this is dimethyl sulfoxide. And notice the plus sign on sulfur and the minus sign on oxygen. That means there is a formal negative charge on oxygen and a formal positive charge on sulfur. This is an electrostatic map. Areas of red indicate a buildup of negative charge. Areas of blue indicate a buildup of positive charge. You will need to be able to figure out a formal charge for atoms in a given molecule. And the way you do that is you use this equation. And what we want to do is count up the number of valence electrons in the free atom and then subtract the number of valence electrons in the bonded atom. And the way we figure out the number of valence electrons in the bonded atom is to subtract the number of bonding electrons divided by 2 and the number of non-bonding electrons. This chart summarizes common formal charges for carbon, nitrogen, oxygen, sulfur, and phosphorus based on how many bonds they have. And so if you look through here, it gives the valence electrons, which will always be the same as what the group number is for the element. And then depending on the bonds and the non-bonding electrons, you use the formula to get to the formal charge. But let's try this. So let's calculate the formal charges on the 4 oxygen atoms in this methyl phosphate dianion. So again, you're going to take the number of valence electrons, so you're just going to look up the group number of the element, minus the number of bonding electrons divided by 2, minus the number of non-bonding electrons. So you may want to pause the video and try to do this on your own for each oxygen atom. So for oxygen 1, you look up the group number for oxygen at 6. So it has 6 valence electrons. Now it has 2 bonds, or 4 bonding electrons. So you take 4 divided by 2, and then it has a total of 4 non-bonding electrons. So when you take 6 minus 4 divided by 2 minus 4, you get 0. So for oxygen 1, that has a 0 formal charge. For oxygen 2, you start with the same number of valence electrons, 6, minus, it has 2 bonds, which would be 4 shared electrons. Divide that by 2, minus the number of non-bonding electrons, which is 4, and you get to 0. For oxygen 3, you have a valence electron of 6. For oxygen, it's always going to be 6 valence electrons because oxygen's in group 6. Minus, you've got 2 bonding electrons divided by 2, minus a total of 6 non-bonding electrons gives you a -1. So that oxygen has a -1 formal charge. Then finally, for oxygen 4, take 6 valence electrons minus 2 bonded electrons divided by 2 minus 6 gives you a -1. So overall, the formal charge of oxygen atoms 1 and 2 is 0, and of atoms 3 and 4 is -1 on each of those atoms. The final topic is resonance. This can be quite a confusing topic. The issue in resonance is that some molecules have structures that cannot be shown with a single representation. This is where we get to the limits of drawing these Lewis structures to represent molecules, is that in some cases one structure by itself doesn't accurately tell us about where the electrons really are in the molecule. So in certain cases we actually have to draw more than one structure because the actual structure in reality is some hybrid of the 2 or more structures. And these structures are called resonance structures, and they're going to only differ in the position of the pi bond or the lone pair. So these are resonance structures, and the difference between them is that this lone pair has become the pi bond here, and this pi bond became the additional lone pair on the oxygen atom. So we had a movement of the green lone pair and the pi bond between the 2 structures. So a resonance hybrid is just like you would see here with dogs. It's a mixing of 2 different things to give an overall hybrid. So this is ozone. It has 2 resonance structures. So notice the difference between the 2. On the left, we've got the double bond between the two oxygens here on the right, that double bond moved its place. So now it's between the other two oxygens. And then also a lone pair moved. So you'll notice in this one there's 2 lone pairs on this oxygen and 3 on this oxygen, but now that is reversed in the other structure. There are now 3 lone pairs on the left oxygen and 2 lone pairs on the right oxygen. So we had a movement of a pi bond and of a lone pair. They essentially swapped places. Now, an important thing is that in ozone or any structure that has resonance, it's not that it's actually alternating between these 2 different forms, it's that it's some hybrid of these forms. So what it actually looks like could be represented like this, where there's a partial double bond between the oxygen on the left and the center oxygen, as well as the oxygen on the right and the center oxygen. So it's this strange mixture of both structures. Benzene is another example that has 2 resonance forms. So here they are shown. So you'll notice here is that the pi bonds have just all moved places. And again, it's not that benzene is alternating between those 2 structures. It's that what it actually looks like is the hybrid of those 2. But we draw out the individual structures with this special double-headed arrow indicating resonance to indicate that neither structure by itself is right. It's this mishmash of both of them. So some rules for resonance forms. First of all, individual resonance forms are imaginary. The real structure is a hybrid of the different forms. And resonance forms will always only differ in their placement of their pi or non-bonding electrons. And we also use curved arrows to indicate the movement of electrons, but that doesn't mean that the structures are exchanging between those 2 forms. It is just a formalism that we use. So here's an example. Here are 2 resonance structures for something called the acetone anion. So here we have the lone pair on this carbon becoming a pi bond between it and the adjacent carbon, and then we have the pi bond going away and forming a 3rd lone pair on the oxygen. So which structure is not a resonance structure of this ion? Is it A, B, or C? Pause the video and see if you can figure out which one could not be a resonance structure. So the correct answer is B, cannot be a resonance structure. Notice what's different. I actually changed the order of the atoms. So in resonance structure, you're not changing any atom connectivity, you're just moving pi electrons and non-bonding electrons. Finally, it's important to know that different resonance forms of a substance do not have to be equivalent. So you could have one resonance structure that's actually more stable than another. And in the hybrid, that hybrid would look more like the more stable form. Also, resonance structures must obey the normal rules for drawing Lewis structures. So you can't have more than an octet for second row elements. The resonance hybrid is more stable than any individual form, and the resonance forms differ only in the placement of their pi or non-bonding electrons. In the next video, we will tackle the difficult task of actually trying to draw resonance structures.